So before 1893, the way chemists used to write various formulas was CO, Cl3, and then he would put a little dot and say 6NH3. So if I was going to prepare this particular complex, I would need a particular amount of cobalt chloride, and I would need 6 equivalents of ammonia. This particular complex is orange. If I took the same cobalt chloride and changed our synthetic preparation and used 5 equivalents of ammonia, we would get a color that's purple. If I take this COCl3 complex and use 4 equivalents of ammonia, I, in one case, can get green. And if we prepare this complex in a different way, or maybe use a different synthetic procedure, we can have this same complex right here with 4 equivalents of ammonia, and we'll get more of a violet color. The question is, why are these different? And what is responsible for the difference in color here? Because we have a couple complexes, and what's it matter in terms of the way you prepare these? If I prepare something at a low temperature versus a high temperature, should I get the same thing? How can I manipulate the synthetic procedure to manipulate the colors? And you're going to go into detail in your lab this week looking at this synthetic procedure, looking at what we can do to verify whether or not these are the complexes we're looking at versus some type of modern day formula that we come up with now. One of the things that a chemist named Alfred Werner came up with was, he kind of said, well, if these two are exactly the same and they're different, if we write the formulas exactly the same and get different colors, maybe we should be writing our formulas a little bit differently. So in 1893, Werner proposed a theory successfully explaining the differences in color for various transition metal complexes. This is the same theory that we use today. And what his theory focused on was the bonding around the transition metal. So for example, if we look at the compound COCl3.6NH3, and if we assume that cobalt is the transition metal center, we could potentially surround this cobalt with 9 different ligands. So there's 9 different ligands available for bonding. If you think back from chapter 8 and chapter 9 in our textbook, do you guys remember talking about any shapes that we discussed that have 9, a central atom with 9 different surrounding atoms in it? If you think of the common shapes, the Vesper shapes, right? We have linear, we have trigonal pyramid, we have a tetrahedron, we have an octahedron, but we never really talked about something with 9 different species bonded to it. And that's because these shapes, that's a very odd shape to have. And it's not a very common one. So basically, what we can kind of look at here is if I make this particular complex, and then I dissolve it in water, I can figure out what exactly is bound to that particular transition metal and what is going to be, maybe, as Werner proposed, to be a counter ion. Okay? So if I take this and dissolve this into an aqueous solution, what is going to be the identity of this cobalt complex ion, and what are the other spectator ions going to be? These ions in solution can either be Cl minus or they could be NH3. If I have a particular solution right here containing all of these species, how could I tell or how could I prove if there were chloride ions in there versus ammonia? What's some type of reagent that we could look at to determine this? What's that?
Silver.
Silver would be perfect, right? If we add silver into this solution, so if we add silver or silver nitrate and I dump it into this solution, one of two things would happen. One, we could have a silver chloride solid, or the second thing that could happen is we could form this Ag NH3 2+ complex ion. And we learned this from our qualitative analysis scheme. You've seen evidence of these particular reactions. So what we can determine is experimentally, and from these results, we can experimentally determine the number of Cl minus ions in the solution. And what we find is that there are 3 equivalents of Cl minus ions in solution, and there's 0 NH3 in solution. So this can tell us a lot about the identity of what that complex ion is.